All right. Today we are going to be going through the 2026 AP Physics 1 free response questions. It's going through what the answers most likely are going to be. All right, we will start with number 1. So, water exits the nozzle with fountain at an angle theta naught above the horizontal. At time t0, t equals 0, a droplet of water exits the nozzle and follows the path shown and reaches a maximum height h1 above the nozzle. At time tf, the droplet returns to the same height at which the droplet exited the nozzle. Okay, so this looks like a projectile motion scenario with maybe some fluids, since we're looking at water sort of projectiling up to its height and then coming back down. On the axis shown in figure 2, sketch graphs of the horizontal and vertical components of the velocity of the water drop. Okay, so we know for projectile motion that the horizontal velocity is always constant since the force diagram would just be a vertical force downwards due to gravity. So we're going to draw a constant horizontal velocity all the way to TF. And for the vertical velocity, it should start out with a positive value, get to 0 about halfway through its motion, then continue with that same negative acceleration towards that final value of TF. So we'll draw that pretty symmetrically, right around the middle. That looks pretty good. And the acceleration, the slope of that line should be about negative 9.8 meters per second squared. All right. Part double I, derive an expression for the speed of the water exiting the nozzle. Express your final answer in terms of theta naught h1 of physical constants as appropriate. Perfect. And then, of course, we need to begin our derivation by writing a fundamental physics principle or equation for the reference information. Okay, let's do that on a separate page. So if we think about what's going on here, our water droplet is exiting at a velocity of v naught, an angle theta naught, and immediately we can already start to think about how that's going to sort of break up into components. So if I draw that over here, we're going to have a horizontal component, which is v naught cosine of theta naught, and then a vertical component that is v naught sine of theta naught. And that's going to be our initial vertical velocity and our initial horizontal velocity. All right, so now if we think about the vertical motion here, this droplet is going to reach a maximum height h1. So we'll say our vertical displacement happens to be a positive h1. Our vertical acceleration should be negative g. Our initial vertical velocity is going to be that vertical component, which is v naught sine of theta naught. And then our final vertical velocity should be 0. So I think to do this derivation, we're going to want to start with that third equation on the reference sheet, v squared equals v naught squared plus 2a delta x. So in this particular case, our final velocity is going to be 0. Our initial velocity is going to be v naught times the sine of theta naught. And then 2 times negative g times positive h1. That should be everything we need to solve this. So we'll say negative v naught squared times the sine of theta naught squared is equal to negative 2g h1. So v naught squared is equal to 2g h1 over sine squared of theta naught. So v naught is equal to square root of 2g h1 divided by the sine of theta naught squared. That should be an expression that has g, h1, and theta naught, with g being the physical constant. Perfect. All right. On to triple I. Triple I says the nozzle has a circular cross section with a radius r naught. Derive an expression for the volume flow rate of water exiting the nozzle. Express your final answer in terms of theta naught, h1, and r naught. Physical constants as appropriate. Okay. So the volume flow rate should just be the cross-sectional area times the speed, horizontal speed. In that particular case here, it's going to be pi times r naught squared, since we're dealing with a circular opening, and that's the cross-sectional area for a circle, times our initial velocity, which should just be pi r naught squared times the square root of 2gh1, h1 over sine squared of theta naught. And I think that is our answer. Perfect. All right. Part B. The fountain nozzle is replaced with a new nozzle of a radius smaller than r naught. It's probably going to be important for later. Water exits the new nozzle at the same angle. The horizontal and the volume flow rate of the water is equal to the volume flow rate of the water of the new nozzle. So same volume flow rate, perfect. So same value of cross-sectional area times speed. A water droplet exiting the new nozzle reaches the maximum height h2. Okay, so if the cross-sectional area goes down, but the volume flow rate stays constant, then that probably means the speed of the water exiting is going to increase. The larger speed should mean larger initial vertical velocity components and horizontal velocity components, and that should cause it to get to a higher height. So I do believe h2 is going to be greater than h1. So we'll start there. So we'll say, because the volume flow rate is the same, by decreasing the radius, we are decreasing the cross-sectional area. Making the velocity in the second case be faster. Because of this, with a faster exit velocity, faster initial velocity, the initial vertical velocity component will be larger. Will be faster. And given how projectile motion works with the same acceleration, the height in the second case should be larger than the height in the first case, the final height. Perfect. That should be good. So yeah, lower cross-sectional area, faster velocity because the volume flow rate is the same, faster initial velocity, larger vertical component, higher heights. This is also true due to conservation of energy as well. Since more kinetic energy will lead to more gravitational potential, you can probably add that as well. This is also true. Probably not needed. Kinetic energy will lead to more final gravitational energy. And a larger value for H2.